1 o'clock on a Monday afternoon in wonderful Hawaii, and you are watching Think Tech Hawaii Research in Manoa. I'm your host, Pete McGinnis-Mark, and today we have a special guest, Casey Hunnemal, who is a graduate student at the Hawaii Institute of Geophysics and Planetology at UH Manoa. And Casey, welcome. It's a pleasure to have you here. And I believe you're a graduate student with a very special set of interests in that you're an instrument engineer.
Yes.
And you've been participating in an astronomy experiment, but not as would be expected at Mauna Kea. You actually go to Antarctica to do your astronomy. Okay, so can you just give us a little bit of an introduction? What is it that took you to Antarctica to be an astronomer or an engineer?
So as an undergraduate at the University of Arizona, I started working on an instrument called the Stratospheric Terahertz Observatory. And it's a high-altitude balloon telescope that flies at 120,000 feet in the stratosphere above Antarctica. And it looks at the Milky Way galaxy, studying the molecular clouds and star formation.
Okay, and people here in Hawaii will be familiar with optical telescopes. You say it's a terahertz instrument.
Yes.
So you're looking at a different portion of the spectrum, is that correct?
Yeah, so instead of looking at light that we can see with our eyes, we look at what we call the far infrared or the terahertz, which is way beyond what we can actually see, and it's more of what you hear on the radio.
Okay, and what is it you were looking at?
We were looking at a carbon and nitrogen in the Milky Way galaxy in the interstellar medium.
Okay, you're just looking at the Milky Way galaxy, so you're not staring out to the remnants of the Big Bang or anything like that, or not comparing one galaxy to another. But how much of the Milky Way galaxy were you able to observe?
So while we're in Antarctica, we look at about 1/4 of the southern Milky Way galaxy, and we did a survey.
Okay, and you'll be telling us, I suspect, how much you were able to observe or how long the telescope was airborne and that sort of thing.
Yeah, so the telescope launched right before December 5th, and it floated at altitude at 120,000 feet for 2 weeks around the Antarctic.
And you're an engineer, you're becoming skilled in building instruments as opposed to being a scientist who actually analyzes those data, is that correct?
That's correct.
Okay. Let's take a look at the first image, because when you're talking about a terahertz observatory, it's really hard for me to imagine what it is. So here for our viewers, can you just describe what it is that you're looking at?
So this is the Stratospheric Terahertz Observatory, and you can see the big panels on the side are our solar arrays, and that's how we get most of our power to recharge our batteries to keep the telescope running. The gold thing in the center is an optical 80-centimeter telescope, and then there's a white cryostat at the bottom that looks like a ball, sort of.
And a cryostat, was it cooled?
It was cooled with liquid helium down.
And why is that? Why do you need cooling?
We cool our instruments so that when our receivers need to be very, very cold at 4 Kelvin or minus 269 Celsius, so that the noise from the receivers doesn't interfere with the signal from the galaxy.
This improves the signal-to-noise capability of the instrument, but minus 269 centigrade is very, very cold. It must be a challenge building an instrument that works at those temperatures.
It is very challenging. We have to make sure that the liquid helium isn't being vented to the atmosphere, or that the cryostat that holds the liquid helium isn't leaking in any way, so it's under a vacuum. And then
and all this to look at the molecular structure of part of our own Milky Way galaxy, correct?
Yes.
Right.
Yes.
And you as a graduate student, presumably you're not the only person. I believe the second image will show us part of the team. Here we are. Where are you? And are you wearing one of the standard red Antarctica jackets there?
This was actually the day before the launch, and I'm actually not there this year. I was there the previous year and this year, but not for the launch.
So you've been to Antarctica twice.
Yes.
We'll get to working in Antarctica in the second part of this show, but that sounds really exciting. Let's take another look. So you were, in the next slide, I believe, you were part of the data reception team?
Yeah, so while I was down in Antarctica, right after they had launched the telescope, I went down and I learned how to control the telescope and how to tell it what to look at. So I basically controlled and drove the telescope.
But why go all the way to Antarctica to just sit in a computer console? I mean, it sounds crazy. You could do this from your office at Manoa, couldn't you?
Yeah, so we can do it from the mainland or from Hawaii, but while we're in Antarctica, we have a better connection to the telescope than you do if you're somewhere else off continent. So it's easier for us to communicate with the telescope while we're down there.
And when you say connection, that's an electronic connection, not on cables or anything like that.
Yeah, it's like Wi-Fi.
It's just like Wi-Fi.
Yeah.
But you have to bounce it all the way from Antarctica back to the mainland and then
up to the telescope. We send our commands from Antarctica to a place in Texas, and then from Texas it goes up to a satellite and then goes down to the telescope. But we still have a better connection.
That's remarkable. And then off screen you were telling me also you have to be there in case the telescope lands earlier than expected or something like that. So
in case anything happens with the telescope, we need to be down there to coordinate with a bunch of the long duration balloon facility workers that control when you drop the balloon and where. And so we have to coordinate with them and also people that work for the Antarctic Treaty to make sure we don't drop it in a very sacred part.
The penguins don't like it, in other words, yes. And it must be a really challenging task to not only have the instrument working correctly, but just to launch a balloon in Antarctica where it's really cold even during the summer, correct?
Yeah. So the biggest problem is the wind shear. So before we launch,
wind moving at different levels in different directions.
Yeah, so we launch two smaller balloons and we tether them together. So you have one balloon down here and a balloon up higher, and you can see whether or not the two balloons are moving in different directions or how calm the weather is. Because if there's any sort of differential movement of the balloons, you can't launch the balloon.
And I believe we got a picture of the launching of the balloon. We'll see a video in a few minutes, but I recognize Mount Erebus in the background, which is very scenic, but the balloon is how big?
When the balloon is fully inflated, it's the size of a football stadium.
Amazing. And that's filled with helium?
Filled with helium, yep.
Which is also difficult to work with in those sort of conditions, okay? And then the image on the right-hand side, that's showing that the telescope, I think that's the correct term, is being suspended on a long tether from the balloon. Is the balloon that size all the way up, or
no,
what happens with the changing atmospheric pressure?
As the balloon goes through the atmosphere, you see that there's a kind of a red tether at the bottom. That all of the white tether is the balloon. So the balloon will take up all of that tether, and then there's the red parachute right there. And that is where the tether really starts for the telescope.
And the parachute is obviously how you retrieve the instrument if you're lucky, right?
Exactly.
and I believe they were able to...
Yeah, we actually were able to drop the balloon telescope on this South Pole Antarctic traverse. So on their way back from the South Pole, they picked up the balloon.
This sounds really exciting to me. Let's take a look at the next slide. And for our viewers, what we're looking at, I presume, is a satellite view of Antarctica. And Casey, tell us what exactly we're seeing with the blue and the red lines.
So the blue line is our first trip around Antarctica, and you can see where the blue line starts. That is actually where we launched from. And so it went around the South Pole, made a couple loops, and then the red line is where the second loop started. And it ends on top of the blue line, you can kind of see.
And for those viewers who are not that familiar with the scale of Antarctica, we're looking at a continent-size landform, which is bigger than the United States, for example. So this balloon must have gone thousands of kilometers, right?
Yes.
And all those little swirly squiggles, particularly in the red line, is that due to changes in the wind direction, or were you able to control the path of the balloon?
So we can't control the path of the balloon. It just follows the polar vortex that it circles around Antarctica and around the South Pole. So whatever the winds are doing, the balloon's going to do.
sounds really scary if you've invested years of your life building this instrument.
Yes.
And you just let it go.
Yeah.
Okay. And speaking of letting it go, I believe you've brought along to show our viewers actually how you launch this balloon.
Yes.
Can we run the video? And Casey, can you just give us a description of what it is we're seeing? This one's for about 2 minutes, so
Yeah.
hold your breath. But what is it we're looking at here?
So you can see that this is the balloon on the launch pad out in at the long duration balloon facility. You can see on the left side that there's a tiny white speck. That's one of the weather balloons that we use to monitor the weather.
Up towards the top left.
Yes. And then you can see that the large balloon, the high altitude balloon, is being filled with liquid helium. And one of the helium fill lines is actually floating in the wind, if you can kind of see it. And pretty soon, they'll let the balloon go, and it'll float up. And if you look down,
there we go.
There it goes. So you'll see it rise up, and as soon as it's parallel or perpendicular to the surface of Antarctica, or straight up and down, they'll release the telescope.
And of course, the balloon looks as if it's just about to collapse. It's not fully inflated because as it's rising,
it will inflate more.
It will inflate more and more, even though it's got the same amount of helium in it.
Yeah. So pretty soon it'll be straight up and down above the telescope, and they'll release it from the launch vehicle.
And it's fortunate you can do this during the daytime.
Yeah.
If you had to do optical observatory, you'd have to be there at nighttime, right? Which would be much colder.
It would be actually much harder because during this time, during the Antarctic summer, the sun never sets.
And I guess we're soon going to get liftoff. It's a very slow process.
Right there. Yep.
Right there, it's taking off. Very slow process because presumably you only get one chance to.
You only get one chance.
And how much is that telescope worth? Any idea?
A couple million.
A couple of $1 million and a few graduate degrees.
Yes,
to boot,
we
right?
had about 5 graduate students work on this project.
About 5. And this was when you were working at the University of Arizona, correct?
Yes.
So you've come to Manoa and you're still building instruments and you're working on data analysis. But this particular baby, which we're seeing lifting into the sky, this included investigators and graduate students from the University of Arizona. And what was your feeling when you see this?
I was very thankful that we finally got to launch. The first year we went down, we had such bad weather that there was no chance of launching. So we were very fortunate that NASA and the NSF allowed us to go down a second year when we had perfect weather and we were able to launch.
Yeah, see, when I was in Antarctica, we had whiteout days and we had really strong winds. This looks to be quite idyllic in comparison to what I remember. That looks really interesting. And of course, you're collecting new science data which astronomers might be working on for years, would be my guess, is that?
Yeah, we're creating 3-dimensional maps of the Milky Way galaxy.
And that tells you what?
We can look at the turbulence inside the interstellar medium, energy balance. We can also look at star formation rates, and this helps us to connect the life cycle of the interstellar medium and star formation.
Can you see individual stars with this telescope, or is it star clusters, the sort of things Hubble telescope can observe?
I'm actually not sure. I haven't actually had any chance to look at the data that has come from the telescope.
You just build the instrument and work on getting the data back, which is a really important thing, particularly for a graduate student to be working on. Okay, well, when we come back, I'm going to ask you a bit more about life in Antarctica, but let me just remind the viewers, you are watching Think Tech Hawaii, Research in Manoa. I'm your host, Pete McGuinness-Mark, and today our guest is Casey Hannibal, who is an engineer, instrument development graduate student at the University of Hawaii, and we'll be right back.
Hello, I'm Dean Nelson, host of Planet of the Courageous. From a Tibetan point of view, we chose to be on this planet because we enrolled in a sort of graduate school for courage. Just that we may have chosen this adventure is a leap of logic. The question is, how do we spend and make sense of this precious human life? We are, as a species, extraordinarily successful, dominating the planet, and now with planetary-sized problems that our existence itself has created. It takes courage to face not only the uncertainty of life, but also the challenge of sustaining the gift of life for future generations. Join us every other Monday at 3 p.m. on Think Tech Hawaii. Aloha.
Hi everyone, Ted Ralston here, host of our Think Tech show Where the Drone Leads, and a lot of you, of course, have been setting your clocks at 4 o'clock on Friday so that you can make sure you see our show. It's now changed. It's now going to be at noon on Thursdays. Noon on Thursdays, new standard time for Where the Drone Leads, and Where the Drone Leads is to systems like this, capabilities that we're using here in Hawaii these days, and we need you to pay attention to this, be part of it. So see you at noon on Thursdays.
And welcome back. You're watching Think Tech Hawaii, Research in Manoa. I'm your host, Pete McGinnis-Mark, and today's guest is Casey Hannibal, who is a graduate research assistant at the University of Hawaii at Manoa. And Casey, before the break, you showed us this wonderful video, as well as some slides of the instrument that you were building or working on the data collection. But it must be fabulous for a graduate student to go down to Antarctica. Is that true?
Oh, it was definitely an experience.
Yeah.
Once in a lifetime, really.
Except you've been twice.
Except I've been twice.
Wonderful. Now, well, yeah, we have a picture of you standing by a plaque in Antarctica. There you go. And so you were visiting McMurdo Station.
Yep.
And it looks as if this is sponsored by the National Science Foundation. Is that correct?
It is.
What sort of place is McMurdo?
It's like a big town, but small. Only about 1,000 people are there during the summertime, and then during the wintertime it drops down to 200 people just to keep the base and the station running.
And presumably it's quite cold.
Very cold. Actually, but during the summertime, I could take off my jacket and walk around in a short sleeve shirt.
Really?
Colorado was actually colder at some times during the time I was there.
Okay, but I presume when I was there, I went on to the high plateau in Antarctica where the temperatures dropped to like -40 or something like that. So it's really cold.
I actually never experienced anything below -20 when I was there.
All right, okay. And there's other pictures that we can look at. So here's a split screen of two different views. What are we looking at here?
So on the left, we can see Discovery Hut, which is where Scott, Scott's
yes, Scott of the Antarctic. He set off for the South Pole from this hut, correct?
Right, and that's where they lived. And then in the background, you can see McMurdo Station, and you can see some of the dorms that you actually live in. And then on the right, you can see more of the landscape and the part of the Ross Ice Shelf.
Okay, I always thought McMurdo was more like a construction site. For our viewers who've never seen it before, it's really chaotic. It's not like Manoa or anywhere we're familiar with here in Hawaii.
Yeah, you do have to be careful because there is a lot of big vehicles moving around, moving heavy equipment, but I felt it was pretty town-like.
Pretty town,
Yeah.
And do they have like restaurants there or or cafeterias or?
There's the galley, which is the one cafeteria. They make breakfast, lunch, and dinner for you. Then they have 3 bars technically, but you can't get food at them.
Okay, so you were there for how many days?
In total, on both trips, I was there for about 60 days.
Okay. And how do you get there?
So
That must be fun, right?
Yeah, in order to get there, I took a commercial flight from Hawaii to Christchurch, New Zealand, which meant that I had to stop in Sydney, Australia. And then from Christchurch, I took the LC-130, the Hercules military plane, from Christchurch to Antarctica, which was an 8-hour flight.
And are there airports in Antarctica, or where do you land?
We land on the Ross Ice Shelf. So the plane has skis underneath it, and along with the wheels, so that's how they land on the ice.
And you just hope that the ice doesn't melt before your plane takes off, right?
On the Ross Ice Shelf doesn't melt as frequently, and they groom it so that it's like a runway.
Did you notice when we were talking about the ice sheet melting with global climate change? Is there any concern about ice in Antarctica melting? So
Yeah, the biggest issue for global warming is the penguins. The penguin population is diminishing.
Okay.
when I was there the first year, I was there long enough that I could start to see the Ross Ice Shelf melt, which was on time. But then this year it melted a lot later, so I didn't get to see it. And so the penguins never came.
Oh,
And so
too bad.
it's, yeah,
Too
I
bad.
saw,
As
I
a
saw
tourist,
one penguin,
yes,
but
yes.
yeah.
And I believe there's one more slide. Let's take a look at this. And this looks quite mountainous.
Yeah, it's quite beautiful up there. That is actually an image of Hut Point Cross, and then you can see McMurdo Sound in the background.
Because this part of Antarctica, McMurdo Station, wasn't this where both Scott and Shackleton were in the early 20th century? So there must be a lot of history.
Yes, there's a lot of history. It's actually pretty neat because you can hike out to Discovery Hut and you can actually go inside of it on certain days and see all of the things that they left behind that has been preserved.
The frozen supplies.
The frozen, and there's even a dead seal outside the door that they were eating when they ran out of food.
It was closed when I was there.
Oh,
Too bad.
that's unfortunate.
But now, Casey, you're a graduate student.
Yes.
How do you get to do all this exciting kind of traveling and research? What skill sets are you good at?
I am really good at working with my hands and building and fixing things. And I just kind of got lucky. I stumbled into a job that taught me how to solder and make computer boards and PCB parts. So I learned that I wanted to work with my hands and build instruments, and I just pursued that.
Right. And even though the original work with this telescope was done in Arizona, you've now started a graduate program here in Hawaii at UH Manoa. Tell me a little bit, what is it that you're doing there which is different? You're not an astronomer. You build or you instruments or you analyze those data sets. Is that correct?
Yeah, so now as a graduate student here, I am building a hyperspectral infrared detector that looks at gas plumes from the Kilauea volcano. So
hyperspectral.
It's high resolution.
In terms of the size of the object you can see, or the individual wavelengths of light?
In terms of the individual wavelengths of light that we can gather.
And as a graduate student, you get to be involved with building this kind of instrument?
Yes. So I've actually built the instrument and I've tested it to determine its sensitivity and how well it will work out in the field.
And you're measuring volcanic gases.
Yes.
So this is something quite new compared to radio astronomy, right?
Yeah.
What would you hope to do once you graduate? Are there any jobs in this kind of field or what?
My ultimate goal is to become an astronaut.
Oh, really? Terrific. Okay.
Yes.
And I believe when you were at a conference in Houston in March, right?
Yes.
Didn't you get to talk to astronauts?
I got to talk to 2 astronauts. I met Jack Schmidt, who was the first and last geologist to walk on the moon.
Unbelievable.
Yeah.
Okay, he must be a really interesting guy to talk to then.
He was definitely interesting, and it was a lot of fun to meet him.
And what sort of discussion could you have with an astronaut? I know if I met an astronaut, I wouldn't know what to say to this person. Particularly one of the 12 who've actually walked on the moon.
I had to think of a lot of questions to ask him, but the main one I wanted to ask was what color looks like in space, because it looks different than it does here on Earth because there's no atmosphere. And his response was that it was just so much more vibrant.
How interesting. So the colors on the moon, it seems to be a very gray planetary body, right?
But like they have the American flag on their arm.
Yes.
And so if they can see that, then, or like the American flag that they put on the moon, yeah. So the colors are very vibrant apparently. And
did Jack give you any pointers on how to become an astronaut?
He did, and also I met Dean Epler, who does space suit testing, and both of them were great insights on things that I can do and should be doing to make that goal come true.
Now, there's a high probability that in your career there might actually be astronauts walking not only on the moon, but conceivably going back to Mars, right, or going to Mars.
Yeah.
For the first time. Is that part of your career goal, or? Yeah?
Yes, I would absolutely love to do that.
Okay, and that means that what kind of classes do you take at Manoa? How do you train to be an astronaut candidate?
The main thing about becoming an astronaut is that you do something that you enjoy. And because if you enjoy it, you're going to excel at it. And if you excel at it, you have a better chance of getting a position. So they look for astronauts to be well versed in multiple things and have multiple interests so that when you are training for different things, you will be happy. So I take classes that are interesting to me that help broaden my knowledge of sciences. So
Very good. And I'm sure everything breaks in space, or you've got to be prepared if it breaks in space. So having the engineering and the computer background, which you obviously have from what we've seen today, must be a really big advantage for you. Is that correct?
yes, it's definitely a big advantage having the instrumentation side.
Do you have to fly jets as well, like the T-38s?
Yes.
Astronauts fly? That's, yes, I
Yeah.
can see that has a great advantage as well.
Yeah, definitely. I'm actually looking into taking helicopter lessons.
Oh, very helicopter lessons.
Yeah.
Not very useful for the moon, but maybe for Mars, correct?
Maybe.
Well, this is terrific, Casey. I mean, sort of, how long in advance do you have to sort of prepare your resume to be considered? When would you start applying for astronaut candidacy?
So technically I qualify next year when I finish my master's degree and then start the PhD work.
I see.
I'll have the bachelor's and then 3 years professional experience that qualify me.
Okay, and your advisor knows that you want to be an astronaut.
Yeah.
Well, this is terrific. Well, I wish you great success. I mean, I remember when I was a kid seeing the astronauts on the moon, and John Glenn flying and things like that. But to have already met Harrison Schmitt, the last, one of the last astronauts on the moon, as well as talking to all these people designing new space hardware and that sort of thing. So clearly, you're multi-talented. You're doing some engineering, you're doing some data analysis, you're doing some applied science in terms of looking at volcanic gases. It's really impressive. So thank you very much, Casey, for being on the show today. I just wish you every success in the future, and we'll keep track of what you've actually been doing. So let me just summarize. You've been watching Think Tech Hawaii Research in Manoa. I'm Pete McGinnis-Mark, and our guest today has been Casey Hannibal, who, in addition to being an engineer working on astronomy programs in Antarctica, is clearly set to be a future astronaut. So we wish her all the success in that. Let me also remind you that Think Tech Hawaii is seen here every Monday at 1 o'clock Hawaii Standard Time. So without more ado, I hope you'll be joining us again next week. Until then, goodbye.